Hello, my name is Aaron Fisher, and today we will be talking about fusion reactor types, not the reaction of fusion itself, but that will be briefly gone over in this talk. So first we're going to go over a brief history of fusion. Albert Einstein, very important to the development of fusion. We all know who he is, famous German scientist. His equation equals mc squared was a big stepping stone in crossing to nuclear technology. Basically equals mc squared means that energy is equal to the mass times the speed of light squared, which in the speed of light is a very big number. So a small amount of mass times the speed of light can equal a big amount of energy. This was very good, but this was used for nuclear weapons when this was discovered because of World War II, which but then was later used for nuclear power, but specifically fission itself. This process was used as fusion because it was relatable, because they're both nuclear energy. So fusion is a process. The sun itself uses fusion, and fusion is created by two isotopes of hydrogen. Isotopes are atoms that have more than the usual amount of neutrons in them, making them heavier. And in terms of fusion, more weight is more power, which is why they like to use isotopes. And the isotopes they use are deuterium, tritium, isotopes of hydrogen. The fusion in the real world, its purpose is to create energy, and this energy could be a near infinite amount, and this is a great source of energy. The whole world could be ran on fusion if we were able to find a sustainable, usable fusion reaction. So the first reactor we're going to be going over is the tokamak reactor. So tokamak was created by Russian scientists, but the tokamak is unique in how it uses magnetic confinement. Magnetic confinement is also considered one of the best ways to contain a fusion reaction. So magnetic confinement is toroidal in shape. Toroidal means that it's like a donut, and how it does is it creates there's magnets all around the reactor walls, and this reactor wall creates intertwining magnetic fields that basically makes bars. This holds the actual fusion itself reaction so that nothing can escape. This creates a sustained fusion reaction. But along with a lot of other things, tokamak has some few problems. The biggest one is the extreme temperature gradients. The magnets have to be cooled to near close to absolute zero, but then the fusion process itself is thousands upon thousands of degrees Celsius. The next reactor we're going to be going over is the direct drive reactor. This one uses inertial confinement. This one is a bit different than magnetic confinement, but it is still a very good way to produce fusion. So one big part of the direct drive is lasers. These lasers are important as they are what heats up the fusion reaction. But how this relates to inertial confinement is that inertial confinement means that the lasers will shoot at the deuterium and tritium. This actually will cause an explosion along the outside, and the explosion on the outside forces the deuterium and the tritium inward, and this inertia that it creates is actually what holds the fusion reaction together. But like I said, the problem with the direct drive reactor is, from the first picture, that is just the center of the direct drive reactor. But the second picture is the actual laser part. The size of the reactor is huge. It's insanely big. And that could cause inefficiencies with building and maintaining them. So the last reactor we're going to be talking about is the Z-machine. Z-machine is a specific reactor versus the other two, which there are multiple of. The Z-machine was created by Sandia National Laboratories in New Mexico. Sandia National Laboratories is just a national scientific program. They have tons of different projects, but we're going to be going to the Z-machine, which is a specific fusion reactor. Z-machine uses something called magneto-inertial confinement. This is a unique form. This whole reactor is actually the most unique reactor on here. Magneto-inertial confinement uses magnets to create the inertial confinement. Inside the tokamak, there is a tungsten cylinder or contraption holding the deuterium and tritium. Large magnetic pulses push the tungsten to get inward. This tungsten that goes inward creates the heat and it also creates the magnetic force that pushes inward. That creates the reaction. But the biggest flaw with the Z machine is that it is a prototype, so we still don't know much about it, and there are often problems with the reactor. So the importance of fusion itself is that fusion has the potential to be the best energy source. You can create near amounts of fuel with it because hydrogen is so easy to find, and the energy source itself is very clean. There is almost no radiation at all created with this nuclear reactor. But from this chart here, this shows the advantage of fusion between fission. You can see that the energy you get from fusion is much higher than fission, versus when they have roughly the same amount of energy lost at the end. But this makes fusion much more superior, and that is why fusion is one of the best energy sources and it should be used widely.